All right, let's dive right into this paper.
Okay.
Extending language model context up to 3 million tokens on a single GPU. Pretty crazy title, huh?
It's a mouthful.
It is.
But really interesting research.
Yeah, and I think for our audience,
Yeah.
people who are really into the AI space, LLMs, all that.
For sure.
I think this is going to be a really exciting one to break down.
Absolutely. This is kind of pushing the boundaries of what we thought was possible with these LLMs.
Right, and especially that
Yeah.
on a single GPU part.
Exactly. I mean, that's the really impressive part, right? They're achieving these crazy long context lengths without needing specialized hardware.
Yeah, no crazy TPU pods or anything.
Exactly. And without retraining the models.
Right.
Just leveraging what we already have.
And so, I mean, what are some of the things that immediately come to mind when you think about okay, 3 million tokens, what can I do with that?
Well, I mean, imagine analyzing an entire code base in one go.
Oh, wow.
Right. Or understanding a complex research paper without losing track of the key ideas.
Yeah, that's always a problem for me.
Right. Or even having chatbots that remember your entire conversation history.
Okay, yeah.
The possibilities are really mind-blowing.
Yeah, so much potential there.
Yeah.
But obviously longer context lengths mean more memory, more compute.
Exactly. And that's the challenge this paper tackles head on.
Right.
I mean, traditionally, these LLMs just couldn't handle sequences beyond what they were trained on.
And why is that?
Well, a big part of it is the attention mechanism.
Okay.
The way it compares each token to every other token. It leads to this quadratic scaling in both computation and memory as the context length grows.
Right, so it just gets out of control.
It gets really computationally expensive.
Yeah.
And then you have the KV cache, which also grows linearly with context length.
Okay, so you've got kind of this double whammy.
Exactly. A lot of memory demands.
So how are they addressing those things?
So they introduced this new framework called InfiniteHiP.
InfiniteHiP?
Yeah, it's a combination of a few existing techniques, but with some crucial tweaks to get these amazing results.
So what are those techniques?
Well, they use efficient sparse attention, dynamic rope adjustment, and KV cache offloading.
Okay, so let's break those down one by one.
Sure.
Maybe starting with the sparse attention.
Okay, so the key insight here is that attention matrices are actually very sparse.
Sparse.
Yeah. Most tokens in a sequence simply aren't that important for understanding the overall meaning.
Interesting. So it's like cutting out the noise.
Exactly. And that's what InfiniteHiP does.
Okay.
It cleverly prunes away irrelevant tokens to reduce the computational burden.
So how do they know which tokens to prune?
They use a technique called modular hierarchical token pruning.
Modular hierarchical token pruning.
Yeah, it's a bit of a mouthful.
It is.
But essentially, they divide the input sequence into chunks and then use a hierarchical process to identify the most important tokens within each chunk.
So not just randomly discarding.
No, it's very strategic.
Okay, and this pruning must save a ton of computation time, right?
Absolutely. It significantly speeds up the attention mechanism, which is usually the bottleneck in LLMs.
Right.
Especially with long sequences.
So we've got this sparse attention.
Yeah.
What was the next one?
Dynamic rope adjuster.
Dynamic rope adjuster.
So rope, short for rotary position embedding, helps the model understand the order of words in a sequence.
So it's like giving the LLM a sense of grammar.
Yeah, you could think of it that way.
Okay.
Now, traditionally, you'd have to retrain the entire LLM if you wanted to handle sequences longer than what it was originally trained on.
Right.
But InfiniteHiP dynamically adjusts the rope on the fly.
On the fly, okay.
So pre-trained models can handle much longer sequences without any retraining.
So that saves a lot of time and resources.
Exactly.
So you got the sparse attention, the dynamic rope adjustment, and the last one was KV cache offloading.
Right. So this is where they get really clever with memory management.
Okay.
They offload less frequently used parts of the KV cache to the larger host memory.
So they're not keeping everything on the GPU all the time.
Exactly. They're only keeping the most relevant information on the GPU.
Okay, so it's like a dynamic librarian who knows exactly which books to keep on the shelves and which ones to store in the archives.
That's a great analogy. And it's all managed by this least recently used policy.
Least recently used, okay.
So the GPU memory stays clutter-free and the processing remains efficient.
Clever. So you've got these three main techniques walking together to make this whole thing possible.
That's spicely.
And it's all happening on a single, widely available GPU.
That's the beauty of it.
It's really impressive what they've been able to achieve.
I agree. It's a game changer for anyone working with large language models.
Absolutely. Now, I know we've only scratched the surface here.
Yeah.
There's a lot more to unpack.
For sure.
So for all of you listening, stay tuned because we're going to dive deeper into the specifics of how these techniques work, and
Excellent.
what kind of results they're actually getting with InfiniteHiP.
We'll get into the nitty-gritty.
You will.
So before we jump back into the details of this InfiniteHiP framework, I think it's worth reiterating just how impactful this kind of research can be.
For sure, for sure.
I mean, being able to process these super long contexts opens up so many possibilities.
Right, like we were talking about before.
Yeah, analyzing massive code bases, understanding complex research papers, building chatbots that actually remember everything you've said.
Yeah,
It's like game-changing stuff.
It is, it is.
And the fact that they're doing this all on a single GPU, it just makes it even more impressive.
Exactly, exactly.
So let's dig back into how they're actually achieving this.
Okay, yeah, where do we start?
Well, we were talking about the KV cache before.
Right, right.
And how it can become a bottleneck with these long context links.
Yeah, because it grows linearly with the context, right?
Exactly.
Because you've got this huge amount of information that needs to be stored and accessed.
And that's where their clever KV cache offloading comes in.
Okay, remind me how that works again?
So essentially, they treat the GPU memory and the larger host memory as a unified space.
Okay, so it's like having two levels of storage.
Yeah, exactly.
You've got the fast but limited GPU memory, and then the slower but much larger host memory.
Right, and InfiniteHiP constantly shovels information between these two tiers.
So it's like a
based on how frequently it's needed.
Dynamic balancing act.
Yeah, exactly. They use a least recently used policy.
Least recently used.
Which means that the data that hasn't been accessed for the longest time gets moved to the host memory.
To make room for the more active data?
Exactly.
Okay, that's a really smart way to manage all that information.
It is, and it's crucial for allowing them to handle these massive context lengths.
Right, right.
Without running out of memory.
Now, speaking of memory, I'm curious about the overall scalability of this. You know, the paper focuses on a single GPU setup. But could this be extended to multiple GPUs?
It's definitely an area ripe for exploration.
Yeah.
I think the challenge lies in efficiently distributing the workload and managing the communication overhead between devices.
Because you don't want to lose all the speed gains you've made.
Exactly.
Just because you're now coordinating between multiple GPUs.
Right. But if they can figure that out, the potential benefits are enormous.
Yeah, imagine being able to analyze data sets that are just way beyond what we can currently handle.
Orders of magnitude larger.
Yeah, it could revolutionize so many fields.
Absolutely. And it's not just about scale.
Right.
It's also about pushing the limits of context length. Even with this clever offloading, at some point, the size of that KV cache is going to be a limiting factor.
Yeah, it's like
no matter how much memory you have,
fundamental hardware constraint.
Yeah, we might need to explore completely new memory architectures or develop some radical new compression techniques
to truly achieve that infinite context.
Exactly.
That's fascinating. I mean, it really highlights how algorithm development and hardware limitations are so intertwined.
They go hand in hand.
Okay, so we've talked a lot about the technical details, but I want to shift gears a bit and talk about real-world applications.
Sure.
Like, how can this technology actually be used?
Well, I think one area where it could have a huge impact is code analysis.
Code analysis, okay.
Imagine being able to feed an entire code base,
millions of lines of code,
into an LLM and ask it to identify potential bugs or security vulnerabilities.
Oh, wow, that would be incredible.
Or even suggest improvements.
Yeah, it's like having
an AI code reviewer.
Exactly.
What about other applications?
Well, in scientific research, you could analyze massive data sets from experiments or simulations.
Right. In the legal field, you could process entire case histories to find relevant precedents.
Okay, so
the possibilities are really endless.
Anywhere where you have these huge data sets that need to be analyzed.
Exactly.
That's powerful stuff.
It is.
But of course, no technology is perfect.
Yeah.
What are some potential downsides or challenges?
Well, one concern is the computational cost.
Right, even with all the optimizations.
It still requires a lot of computing power.
So it might not be accessible to everyone.
Yeah, that's a potential barrier.
And then there's also the ethical considerations.
Right, giving LLMs access to so much information raises concerns about privacy and bias.
And the potential for misuse.
Exactly, we need to be mindful of those things.
Absolutely, so it's not just about pushing the technological boundary.
It's about...
We also need to think about the ethical implication.
We need to develop the right safeguards.
Right, well said. It's pretty clear that InfiniteHiP is a big step forward for LLMs.
Yeah, no doubt.
But like you said, there are still some challenges and things to think about ethically.
It's true, for sure.
So where do we go from here? Like what's next?
Well, one area that I'm really excited about is multimodal LLMs.
Multimodal?
Yeah, so LLMs that can process not just text, but also images, audio, video, all within a single context.
That's getting really complex.
It is. but the potential is incredible.
Yeah, I mean, imagine an LLM that could analyze a scientific paper, understand the text, interpret the graphs and charts,
Yeah.
even process the audio from a presentation.
Exactly.
That's like a whole new level of understanding.
It is. It's like moving towards a more holistic view of information.
So how would InfiniteHiP fit into this multimodal world?
Well, I think the techniques they've developed,
Okay.
like sparse attention and KV cache offloading, could be adapted to handle other data types as well.
So instead of just pruning irrelevant tokens,
Yeah.
you'd be pruning irrelevant pixels or audio segments.
Exactly.
It would be a challenge, but I think it's definitely possible.
Yeah, I agree.
This multimodal aspect really opens up a whole new dimension
It does.
for long context LLMs.
It's not just about longer text anymore.
Right, it's about understanding how all these different forms of information connect.
It's about building a more complete picture of the world.
It's a pretty exciting time to be following this field.
It is, for sure.
But as we wrap up this deep dive, I want
Yeah.
to leave everyone with a thought.
Okay.
We've talked about the potential of LLMs to change the world, but what about the impact on knowledge itself?
That's a deep one.
I mean, if LLMs can process so much information,
Yeah.
does that change what it means to be knowledgeable?
It's a fundamental question, right?
Yeah.
Like, will we reach a point where human understanding becomes secondary to the insights generated by AI?
It's a bit unsettling to think about,
It is. It's a big question.
but it's one we need to be asking
Absolutely.
as we continue to develop these powerful technologies.
We need to be mindful of the implications.
Yeah, well said.
It's been a great discussion.
It has.
This InfiniteHiP research is really groundbreaking.
It is, and I think it's just the beginning.
I agree.
So for everyone listening, keep exploring this stuff.
Stay curious.
And we'll see you next time for another deep dive into the world of AI.